So G will be a split reductive group over local non-Archimedean fields. So O in these the range of integers. So as usual, H, the Hecker algebra is algebra of function compact support. Compact support which invariant on the left, on the right, by the action of GO on G of F. So this is known to be a commutative algebras, and it is a Satake isomorphism. I can identify it with the algebra of the dual groups. So G hat is complex dual reductive group. So if phi is an irreducible unramified representation, so that means pi has a vector, non-zero vector fixed under the action of G of O. Then we know that H acts by convolution product on this vector space, which can be one-dimensional. And this isomorphism, Satake isomorphism, and so this pi will correspond to some sigma, some semi-simple conjugacy class. In G hat. And the isomorphism has been made in such a way that for every phi in H, you have a trace of on pi of phi. So the trace makes sense because phi as a Hecker function will project this infinite-dimensional space on this one-dimensional vector space. We can take the trace. So this is going to be a phi check of sigma. So this, so now it's an algebraic function which can be evaluated on the sigma, on the conjugacy class. Okay. So now you can try to do something a little bit different. So instead of looking at a regular function in G hat, you can look at some interesting rational functions. So so if let's sigma irreducible algebraic representation of the dual groups, then one can, following Langlands, one can define the L functions, L factors. So it depends on a complex parameter S, rho, and pi. So it's really about pi, but we have auxiliary parameters S and rho is determinant of 1 minus sigma rho sigma and q to the minus s minus 1, where q is the cardinal of the residue field of the local fields. So this is, let me just denote this by the revision name. this becomes a function from sigma mapped to psi tilde s of sigma. And now psi tilde s can be regarded as a rational function on G hat, which is equivalent, which is invariant in the adjoint action, and depending on one parameter s. So one may ask the question whether one can construct the function. So now psi belongs to a localization of the algebra on the right. So one can ask, so this psi s, one can ask, is there any psi s on the localization left-hand side that would correspond to this function on the right-hand side, right? So for doing that, we can first expand in a single-minded way, simple-minded way. So this is write a sum from 0 to infinity of trace of sim n of rho sigma q to the minus ns. And now this, let me call this thing psi of n, right? So now psi n is a regular function. Then you know it has inverse Adler transforms. And so we can, of course, let psi s to be this infinite sum, at least formally, of psi. This, let me call this psi tilde n to be consistent. And this becomes psi n q to the minus s, right? And we don't know how to make sense of this yet, but this presumably you can have Adler transform, this psi tilde s, which has to do with the local L factors. Okay, so it is not difficult to prove that when the real property of S is large enough, this series is going to converge. One can make sense of it for large S. But somehow I would like to put oneself in a situation when it just makes sense obviously for any S. So in particular, looking for situations where the function psi, you want just sum of psi n. Makes sense by itself. Don't need to make any kind of limit. So this situation actually has been devised by Braverman and Kashdan. This is a razor. So let me define this Braverman and Kashdan setting. So we are going to put ourselves in the situation as follows. So G will be an extension of Gm by, let's say, semi-simple group. This is not important, but it just assume this is semi-simple. So that it looks like Gn len. So instead of doing this, you can just look at this function and twist the representation by determinant, right? So what we're looking for is the following formula. Trace of psi s on pi is the same as trace of psi on pi tensor with determinant to the s. So for this to be true, you want to have the dual psi in this exact sequence, and actually we want that when you add this condition that if you look at the row of Gn of V rho. So the Bellman-Carson condition is if you restrict rho to the central GM, it becomes the identical map from GM central in G hat to the GM central in GNV. So the condition is rho restrict to GM is identity on GM. So I had to make sense of that, but that's easy to understand what it means. So of course, if this is to be the case, then when you put Cman rho, then and that restricted to GM, then you get the elevation to the nth power of GM, right? And with this situation, with this condition, it implies that the psi n whose Sadeka transform is the trace on the n symmetric power is supported by support of psi n is included in the matrix G in G of F such that the valuation of determinant of G is equal to n. So obviously have these one support. So they will have no trouble to make the sum of them. Then makes sense as functioned on G of F. So which can be obviously left and right invariant by the maximum compact, but which is not compact supported. Okay. So that will be the main topic when we try to understand this function psi geometrically, and also you understand attempt to use it in trace formula. So that the main motto is going to put this function as test function in trace formula. So that I go back to that later. So first of all, let's just come back to this. I mean, historically, this function look very familiar because when G is G and D, and rho is a standard representation of the dual groups, then psi is the characteristic function of G and D, F cap with the matrix of D of O. So it's basically just the characteristic function of the integral matrix. So and this is the single case where the function is simple. There's been another case that has been calculated classically, had to do with GSP, and maybe rho with some standard representation. That was calculated by Satake, and that had been reported in the book of MacDonald. In the MacDonald book, he calculated 2 examples. But I understand Kasseman told me that there is some mistake in the calculation. I mean, had to put some factors. But in this case, in the book of MacDonald, it says just calculate from something, but that is wrong. You have to multiply by another factor. Okay. Okay. Now, the first point I'd like to mention is, in general, we would like to understand what would play the role of this space of matrix, right? To construct this space. So, is there for each row a space that contains matrix? That's easy. Yes, there is a monoid. So there is a monoid. associated with rho. So this can be constructed using the Vinberg theory of monoid. So here I should mention that the theory of algebraic monoid was not started by Vinberg, it was started by people like Renner and Pucha. And also it can be generalized quite vastly. This is so-called theory of spherical varieties. I think that had to do with had to do with L functions ultimately, but I think we do not understand the whole thing yet. But let's look at this case, but the thing I'm going to use is the theorem due to Vinberg. Okay, so in this theory, somehow it's convenient to not to fix G, but to fix G prime and let G vary. So we fix sum is simple, and for simply connected G prime, and you look at consider all couples of G and M, where so G is above. G is an extension of the torus by the fixed G prime, and M is an equivalent embedding, is a normal of phi equivalent embedding of G. And that means the action on the left, on the right of G on itself can be extended to M. And under the assumption, this is actually equivalent to that M is an algebraic monoid. So the left and right action can be extended to multiplication on M.
What is T?
T is a torus, some torus. Oh, here is split, yeah. I think if the group, if it starts up, is not split, maybe you had to look at non-split torus. But there should not be any problem. Yeah.
But G is not necessarily split.
No, here G is split. I assume G is split. Yeah. Yeah. But this can be made. G prime is split. Yeah. Here everything is split, but I think that can be generalized to non-split situation. Okay. So. So there is something technical but important is what Vinberg called the abelianization. So we look at this map G. So M to A. A is so let the K be some base field. So the regular function on M, which is invariant on the left and on the right by the semi-simple group. Where this map, and the monoid is going to be very flat. If this abelianization is flat with a geometric, with reduced geometric fiber. And we restrict ourselves into this setting to assume this, you only look at this monoid for which abelianization is very flat. And in this case, Vinberg proved that there is a universal monoid. Okay. So we think that in Gen dk, the universe should be the matrix. It's not true, it's more complicated. For Gen 2, it's just a matrix. But in general, it's more complicated. It's related to the wonderful compactification of the semi-simple group, for example. And I think the important point is when you, after I recall the construction of Vinberg construction of universal monoid, it will be clear that it had to do with the Hecker algebras. Okay. So construction. Sorry?
You said K is a field?
K is a field, it can be F. Yeah, K is some base field. Base field when you define your group.
So when you say flat, it's flat over what?
No, this map is flat.
That is map.
It's mapped from M to A. Yeah. So actually A is a toric varieties, right? When you A have action of the T, and it can be proved as affine toric varieties. So some of the monoid, the combinatorics of this gadget is kind of mixed between the combinatoric of root system of G prime and combinatoric of toric varieties. It's some kind of tricky combinatorics. Okay, so let me construct one of these monoid and some of the universal one. So let T prime be the maximum torus of G prime and Z prime the center of G prime, and you can put G plus to be G prime times T prime mod Z prime acting diagonally. And so, and then we have this exact sequence to Z plus, to T plus, to 0, where T plus is now T prime mod Z prime, and this becomes the torus of the adjoint groups, and it is Gm to the R, and this map is given by the simple root. So in fixed Borel, then you have simple roots that identify the maximum torus of adjoint group with the product of Gm. And so, of course, this you have alpha I extend to G plus. Now you have the rho I. So let omega 1, omega R be the fundamental weight of G prime. And then you have this fundamental representation of G prime going to GMVI of highest weight omega I. And you want to extend this rho I over G plus. And I mean, I had to try. And the only one way to do it is to write this formula. It looked complicated maybe because I didn't choose the right normalization, but when you try, it's only formula you can write. So that is factorized to the center. Okay. So let's call this alpha plus, and this is rho plus, and then you have this alpha plus, rho plus from G plus to the product of Gm and product of Gn Vi, which can obviously embedded into some this obvious monoid. Matrices. And so Gm plus is defined to be the closure. So this is an embedding, and this is a closure of G plus I mean, in small characteristics, it may happen that m plus is not normal, in which case you want to normalize it. But this is not a, I think, not very important issue. And so what Vinberg proof is this is universal in the sense that for every flat monoid can be obtained by base change from G plus and M plus. So that means you have, just look at M, so we have M plus going to A plus. So this is acted on by T plus. And if you want to construct another monoid, you just look at some T, some character, some homomorphism T from 2 to T plus. That can be extended in a morphic toric variety from A to A plus, then you base change. And that is the recipe to construct any monoid. Okay. So now I want to take 1 minute to explain why this has anything to do with the Heike algebra and Cartan decompositions. It clearly has something to do because if you want that, for example, if you want G to be in K P lambda K, maybe I mean it's easier to write a condition for if you want to look at the union of for on lambda prime less than lambda by the even dominant order. You want to write this condition, and obviously you have to use on these fundamental weight limitation to write down, like the K of G, and then have to write on the minus, right? And now, if you want to write precisely, what you really want is that rho plus of, you just put this to the T, pi lambda and G is actually in the M plus of O, right? So this condition become a condition that something become integral point. So the monoid is just basically that what is how it be used. The condition kind of complicated, some double coset can be expressed, I mean, geometrically as integral point. Okay. So now that has clearly to do with algebras. Now let's come back to the L function. So L function is basically to do with the fact that we want this to be GA and this to be GA, right? So just look at the I mean, in the L function there is this S, so it corresponds to some GM. And so you want to put GM here, and so you want to put A1 here. And just see that GM, this has to be now just a co-characters of T plus, and the further extend to A1, it just means the dominant. So this is some lambda dominant co-character, and it's quite obviously which one you want to choose. You want to choose this one to be the highest weight. Of rho. So when you start with a representative dual group, it has a highest weight. So you just plug it in this Vinberg construction, you get a monoid. and that is the modality we want. And this actually is this mode. So let's call this M row. So then it become M row, and this has been constructed in paper by Braverman and Kashdan. So by what I just explained a little bit before, we see that the function psi is sum of psi m. So the support of psi is by this equivalence. Is easy to check that support of psi is exactly the or at least it can contain, I mean, more or less equals is g of f, cap is m, rho of O. So the support of this function, each of the integral point of some model. This is Cartesian, yes, by construction. Okay. Now, when you have this monoid, you can ask, well, we have the support, what is the function, right? So that is, the function is complicated. I mean, numerically, you know, this function is quite something very complicated because you have to do symmetric power and then have to decompose symmetric power. So this is kind of complicated business. Well, I mean, naively, when you have complicated function, you want to be to the power shift. Right? So I put some kind of conjecture that let L plus of M rho to be the jet space of M rho. So it's defined by the fact that point on this is the point is value in the formal series on M, and one can ask if you check the IC of this on M plus M. Well, this can be defined, but there's some paper literatures by Kashdan and Vinberg, right?
Yeah, there's two papers. The paper by Vinberg and Kashdan, and there's also a paper by Drenfeld.
Okay.
With a different proof of the same thing.
Yes, so it proves that this jet space, locally, is a product of some finite dimensional type with formal distinct. So at least that it is locally. So whether
formally locally. So it's
formal locally.
Yes, it's true that every formal neighborhood is a product of something finite dimensional and an infinite dimensional.
But that, at least at the end of the standard, it doesn't prove that this actually exists, right?
Well, at least on the level of Stokes, I'm not sure that it's.
The stock is okay.
Yes, the function you can define, and actually this conjecture I think is also known.
Okay. At least, okay, so maybe this is known, but this, I see the function, the trace of Frobenius is psi. Okay. So at least, I don't really understand this local space, but
Sorry, what is IC? Excuse me, what is IC?
Well, it's not clear to me yet, but but I explain you something that they do have the IC now.
It's IC of this.
IC of this M L plus M. Okay. Are you happy, Takeshi? Okay, so now let's look at some global model of this. Okay, so now let's see a smooth projective curve over finite field, and so now let E and E prime be principal G bundles on C. So what I can call what is amorphism. So phi from just notational M, each E prime M will be nothing but a section, a global section of M, and twist on the left by E and twist on the right by E prime, right? And look at the thing of a vector bundle, it's exactly the map, a linear map vector bundle. So if you are given yourself monoid, you can define also amorphisms, right?
G bundle, not G prime, G.
G bundles, yeah. You can M have two arcs on the left and the right, you can twist it, and you can compose it also because it's a monoid. So you can compose. And also we should look at M, look at phi such that generically phi lands in G. That means generically it's an isomorphism of bundles. Then obvious global analog of this loop space is the space of a pair of E and phi, where E is G bundle on C, and phi is a M map from E naught to E. So it's generically an isomorphism. Sorry?
E naught is the trivial bundle.
E naught is a trivial bundle, yes. Right. And these have a morphism to, by abelianization, this has obvious map to the same thing for G, EGM, and for A. So what we get here is just the space of a pair of, so this map to the space of a pair of L and of L and maybe alpha, where L is a Lie bundle and alpha is a global section of L. Over the curve, yes. So this is basically just union, not zero, of sim effective divisors on the curve. Okay. So so let me call this Cn. And so X also be decomposed into the union of Xn, which is again mapped to Cn. And I mean, this construction is very standard, I think, in the case of G control Gn len and phi the trivial representation. It is on Gerard's very first paper on geometric lengths. It is a space he considers. And so with this, it's really not difficult to prove that the IC of this space, this global space of so if D belongs to Cn, so D is a sum of Di Ci. So Ci are point and Di is multiplicities. And then you want to restrict the IC of X to the fibers over D. So I can call this map to system name app. So app minus 1 of D is to be a sim Di of some perverse shift A lambda. So A lambda is the perverse shift corresponding to representations. And that would be correspond to Di1 to 1. And then you point collapse, it gets symmetric powers. So this map, so this fact is, the proof can be proven by the same proof in Lomo paper. So give this function. But somehow, for me, maybe it's totally stupid, but I think the kind of interesting point is even if you cannot define, I don't know how to define the IC on the jet locally. This look like a local. That means you can obviously map X to X can be mapped locally to M of O V mod GOV. And stack it if you like to. So let's call this C. And so you see that the trace of Frobenius on the IC of X is the pullback of the product function of psi V locally. So that is kind of, at least for me, indication that there should be the IC here to make sense. And this is psi V local. This map is not really smooth, no chance to be smooth, but it kind of.
Yeah, but it is formally smooth. If you consider a divisor which is concentrated at one point,
yes,
then in the neighborhood of that divisor, this map is formally smooth.
I see.
Which is easy to prove. And so this is actually, so this is why I said that this conjecture is null, because this global statement is really easy, and it kind of implies that local conjecture immediately, because if it's easy to prove this map is formally smooth. It's not formally smooth as a map from all of X to this thing, but in the neighborhood of points which are concentrated, divisors which are concentrated at one point, it is formally smooth.
Okay. Okay, so so this function is seems to have it has nice geometric interpretations. So there is what you really want to do with these functions. Okay, so let me do it. So there is endoscopy proposal of plane length. So let now automorphic representation pi to be product of pi v in a discrete representation is automorphic space. So here you can have the two choice: either you can fix the centron character or fix an eden. I think it's going to fix an eden somewhere. So just to make this space have finite volumes. So assume this representation unramify everywhere. Then you can write that L of S rho pi is the trace of product of psi v on pi tensor determinant to the S. So it's very tempting to put the trace, to look at the trace of product on the psi v on the whole L2 of this. With some, and that would be a kind of sum of L function.
Is it supposed to be convergent in some way?
Well, it is convergent when it can be proven, it can be combinatorial as well. There's issues. I'm not claiming that anything is proven, but on the spectrum, as far as to the spectrum side, you understood the right hand side by on the on the right hand side, the spectrum side, by look of Lapid and Finitz, I understand that they can be proven that this converge up to the vertical line of the trivial representation, the first born of the trivial representation. So it's converge.
So, for example, if you just sum over all hospital representations, this will be convergent.
Probably, but I don't know. Yeah, I expect it. Yes. On the geometric side, it is mysterious, but we do expect that have a geometric side actually by the same kind of very similar construction. You can explain a little bit later. You have nice moduli space that one can work with. So here, what I want to do with this, right? I have this. So using a trace formula, you're not working with just one function. You would like to have a whole space of test function to put the trace formula. One would. So I think we would like to have a Schwarz space depending on rho, and on every place, and this Schwarz space have a very specific element that is the function psi v. So that would replace the usual case when you have this space of function with compact, support, and smooth on G of Fv. And so this kind of rho equal to 0. And then you have the characteristic function of K. And for every rho, I think this, at least as far as I understand, that's what Braverman and Kashan proposed, there should be this Schwarz space depending on rho with this basic function.
Not rho aussi.
Sorry? So this is rho equal to 0. This is rho general, rho? No.
The space?
The space is.
Of rho is 0? No, but rho means.
As this is some kind of Schwarz space that depending on rho.
But rho, what do you mean by rho equals 0 if rho is representation? If rho is a representation, what does it mean rho equals 0? That's the question.
Oh, the trivial representation. Okay. Thank you. And so with this basic function, that makes sense to make the S rho. Right?
It's not allowed to be trivial, it has to be not trivial, but rather.
Not allowed to be trivial.
Because there was a condition that there was this multiplicative group that you wanted to get.
Well, I mean, I just think that I think it just should have some kind of trace formula that apply depending on rho. But Okay, so here I think there's kind of diverging approaches. There's approach by Bavman Kashdan and later I think pursued by Laurent Laforgue, who would like to prove the functional equation of this LS rho P by using the trace formula on geometric size, trace formula on this side, right? And so there needs to be so the geometric size of some function in this place of phi v, where phi is equal to psi almost on place, is a this kind of sum L function. And one would like to go to the L 1 minus S rho of P dual. And here we would like to go to the space of S for the contrarian representative rho check. So there should be something generalized Fourier transforms and between these Schwarz space, and the equality of geometric psi would look like a Poisson summation. I think Laurent has even candidate for this space, if I understand correctly. So that is one proposal. So there's another
Well, what is this tensor product? So you have a tensor product of Schwarz space. So what is this tensor product?
Sorry? Can you say again?
You wrote the tensor product of Schwarz space. So what is this tensor product?
Oh, the tensor will make sense because you have this function, the basic function.
No, next one. So tensor product over V.
Yes, so product over V. And phi V is equal to psi V for almost on V. So, I mean, obviously, one does the Fourier transform will map psi V to the dual psi to make it consistent. Okay, so now beyond endoscopy, I mean, in Langland's approach, he's at least originally, he was not looking at the functional equation. He was more interested in looking at the bonds that appears in this right-hand side. And we hope that we know that in the proving functoriality is more or less equivalent to partitioned automorphic representation into different bags. Bag corresponds to subgroup of the dual group that receive the Langland's parameters, and in which bag you want to put your representation depend on the order of the pawns you get in LS rho. So control the pawn that appears on the right hand side would tell you what to put in different bags. So that is, I mean, naively what would I like to do, and as always, you want to try to use the geometric psi with this complicated function to prove whatever you want to prove on spectron side. But of course, it's rather intimidating because, I mean, for the medical convergence, I mean, you can do not really know how to define this space to start with at the moment. So we can have some kind of long way to go to this. But at least I think that is reasonable proposal, because at least it seems like you have a nice geometric interpretation of the left-hand side. So now let me explain something that I've been trying to do for a couple of years without much success. But okay, so now we have this infinity point in C, and we also choose a map from GM to the center of G, so that you can twist G bundle by divisor, right? So every E bundle, you can do the E of infinity, just for vector bundle. You can twist by one infinity. Okay. So now the quotient of GA mod GF infinity to the Z, the GO, now corresponding to the category of G bundle. But then we decide that the two bundles we just give an isomorphism between these two bundles. So just think about the vector bundle. You can decide that V, you give an isomorphism with V twisted with all infinities. Now, when you look at the geometric side orbital integral, so which is quite easy to guess that you want to look at endomorphism of vector bundle or of bundles. So we look at our space of M is a space of so let E to be an object in this, then the endomorphism of V. So M endomorphisms. M is the E of V, a map from V to Vn infinity, when n go to infinity.
E is V. E is the same as V.
Yeah, it's something as V. Then you look at the space M is a space of E and phi. And phi is just endomorphism of E. So this is to be, you can write this to the limit, which now become E and phi, with now phi map E to E and infinities. So this looks exactly like Hitchin fibration, and you can define it, so that because this Mn, so this, I mean, it's very similar to the Hitchin fibration.
So phi, is it an honest map or is it a map of, is it an M map?
This is M map.
So
Okay, so we want to use so Hitchin fibration have this F to Mn to An, where An using some kind of adjoint quotient of the monoid and built from the adjoint quotient. Mn is this modular space of endomorphism of E bundles.
no, but what is the index N?
N is because I have to add
Oh, it's the same N as over there.
is this N. Adjoint quotient of monoid. And we want to start to study the geometry of trace formula by using this Hitchin fibration. Now the first point, the first issue one can meet is if you put I mean, you have to do with IC because you cannot work with other sheaf, you will not very well. But then what will be the IC of this Mn, right? you just put the IC of this Mn would be the right function, because it's not the same as the space of Xn I defined earlier. But this question seems to be resolved, plus ou moins, by Boutier. I guess. Okay, so now once we get this, well, and then of course here's very much speculation, because even for Hitching vibration, when you start to work with nilpotent cone or hyperbolic space, it's a lot of problem. It's not done yet. I mean, the hyperbolic part has been studied extensively and solved by work of Lomong and Chaudoir. But for nilpotent cone, as far as it's not known. But you can at least expect that in the best of the case, this is completely determined. By the cohomology of the genetic fiber. So this kind of monodrome is so the fiber of this is ability varieties, and we ought to say that the answer is very complicated, but it can be some recipe to write this answer from the representation of monodromy on the H1 of the abelian varieties. And so we would think that then the cohomology of Mn, that is somehow what we are interested in fine, that is trace formula, is somehow kind of should be a cohomology of braid group. I mean, in many cases, it looks like this kind of answer. That is what happens. And of course, then hopefully, beyond endoscopic conjecture of Langlands can be translated into question of stability and cohomology of braid group. That has been studied a lot by topologists. So I mean, the bridge is not built, but I mean, there seems to be one. Okay, thank you.
Thank you. Maybe we start with some questions from Tokyo, then Beijing, and then Paris.
So you braid group? What is this?
Okay. Okay. So the map MN to AN. So how can I look at Takeshi? So should look at this or this? Okay. So the map from MNAN is basically a designation of abelian varieties. So the basic thing you can think about is the family of two covering a projective curve, projective line, right? So that is determined basically by the ramification divisor. Then something bad can happen when the divisor become have multiplicities, right? But before that, the divisor become multiplicity free. You have the nice family of covering, so you have nice family of abelian varieties, Jacobians, and you have representation of the fundamental group on the H1 of that abelian varieties. So that is a very well-known representation of the braid group. That is the braid group on the H1 abelian varieties. And in that case, I think I'm going to prove some kind of stability result when n go to infinities. If you're optimistic enough, there should be something similar in more general situation.
Thank you. Other further question from Tokyo?
So yes, then I'd like to ask about the beyond the endoscopy. So you consider some geometric side. So if we want to compare to geometric side of two groups, then which kind of relations are expected for your test function psi free?
Can you ask? I don't understand what kind of something. I couldn't hear well.
What kind of relation? So in endoscopic case, we expect the matching of orbital integrals, stable orbital integrals.
Yes.
In general case, which kind of relation is expected for?
I mean, it's not really believe that there is a relation between operant agons itself. I mean, in the endoscopic case, that is all. I mean, this kind of very, wonderful case when you have a map between these Schwarz space, and then they just have small agons. But in general, it seems to be rather a transforms, right? The transforms that if you know all operant agons, then you know other operant agons. Just one not determined by one, but by the whole family. It is kind of integral transforms. But in this bioendoscopy approach, as far as I understand it, at least it's not about operant agons. It's about the sum of operant agons, and more precisely, some asymptotic behaviors. So it's not. I mean, it's not really reasonable to try to have any precise answer about this cohomology, but how when n go to infinities, then there should be comparison between two different groups. I mean, this is as precise as I can give as answer for the time being.
No. Yeah, thank you. That's it from Tokyo.
Okay, so we go to Beijing.
Okay. So any questions from Beijing? The speaker? So I think there's no questions from Beijing.
Any questions from there?
So I have a question. Do you expect a closed form answer for this cohomology? So for example, if you really consider the case of trivial row, then basically you're talking about cohomology of Bun-G for which there is a simple answer. So do you believe in kind of similar type answer in general? No.
No, it's a L function. You cannot say nothing about L function, right? The points is much easier things. So the points is kind of asymptotic of the coefficient, right? You like the sum of the Mn is. I mean, in the simplest case, like you just truncate the Dirichlet series, right? You look at the sum of An, Qn up to some big N, and how it grows says something about the points. And that's what we want to compare different groups. And that should be much easier than say about precise value of this.
And one question, do you know anything, or would you like to do anything? I mean, you're only talking about so to say the spherical case here.
Yes.
So do you know anything about smaller complex groups?
Smaller?
I mean, if you consider, because for example, you mentioned the Schwarz space, which should, so, for example, we can prove that it has the same characterization by means of Perot sheaves if you consider its Iwahori part. And conjecturally, it should be the same for the full Schwarz space, although they're not sure how to formulate this precisely. But at least in the Iwahori case, you can do similar analysis. And so, but here you were only talking about computing a trace of some, one particular function, which is invariant.
Oh, but in principle, you have to some place you have to put other functions.
Yeah. So my question is whether you have any conjecture about what, for example, if you put some Iwahori invariant functions, are there any? I mean, here you formulate some kind of vague conjecture about what this cohomology.
I mean, at least about as far as concerned with the points, it's not really important, the local information. I mean, I cannot formulate anything, but I think for Paul's question, it's not local, it's not very relevant.
Other questions? Okay, so there are no other questions. Let's thank the speaker again.